Good morning, everyone. Thank you so much for joining us today. I am so excited about today's talk. My name is Dr. Trena Ferrell, and I am part of the Earth Sciences Division at NASA Goddard Space Flight Center. So once again, welcome. I hope everyone is safe during this pandemic, and I hope everyone's families are also safe. Before we get started, I want to give out some thank yous and some shout outs. First of all, I want to thank our Center Director, Dennis Andrusik, for all of his support, and our senior leaders at NASA Goddard. I also want to thank the Office of Communications under the leadership of Michelle Jones. I want to give a special shout out to Leslie Scott, Daryl De La Rosa, Travis Walrob, Brianna Horton, and Jay O'Leary. It really takes a team to pull off an event like this. In addition, I'd like to give a special shout out to Mark Clampin, the Director of the Earth Sciences at NASA Goddard, and Dr. Jim Irons, the Director of Earth Sciences at NASA Goddard. And also, I'd like to say thank you to Darlene Squibb and to Dr. Karen Moore for helping me with this program as well. So I'm so excited. Hopefully everybody saw the flyer that was being advertised. We are about a week away from Earth Day, the official day, the 22nd. Hopefully everybody saw the flyer. NASA headquarters is offering some special programs next week. So hopefully you can join us for those programs as well. We will also be continuing to have programs here at NASA Goddard. Next week, we have 2 talks. So please join us back again next week for our 2 talks. And also, the Globe Observer app will be having a trees challenge starting on the 15th. So please take out your phones and try to do some citizen science work for us. So without further ado, I'm going to get started and start talking about our great speaker. Everybody loves space and dinosaurs, right? And I'm hoping we've got some kids online today. We want this to be a family affair. Well, I'm excited because we've got Dr. Compton Tucker. He's going to join us. He specializes in studying the Earth with satellites and data. He is among the first researchers to employ first resolution satellite data to exploit the time domain for studying global photosynthesis on land, determining land cover, monitoring droughts, and providing famine early warnings, and predicting ecological coupled disease outbreaks. So we're so excited to have Dr. Compton Tucker with us. He also received a presidential award from President Trump regarding weather in 2017. So maybe you can tell us more, maybe he'll tell us more about that. So I'm going to turn it over to Dr. Compton Tucker. And Compton, I want to thank you again for joining us today and for doing this presentation. So we will be taking questions. We will be answering questions. So if you have any questions, and if you'd like to ask any questions, we'll be answering those questions at the end. So please type them in the chat box. Once again, everyone, thank you for joining us, and get ready. Next week is the official Earth Day celebration. Thank you. Dr. Tucker.
Thanks, Trina, and you're welcome. It's my pleasure to be here. Earth Day is a very special day for us all because, as Carl Sagan said in describing the Earth as a pale blue dot, it's here, it's home, it's us. This is where we make our stand. So I'll be talking about the Earth's climate the past 245 million years. And could I have the first slide, please? This is a general summary of what I'll be talking about over this time span of 245 million years. I'll spend a fair amount of time on the age of reptiles, which is very interesting. Then I'll make the transition to the Milankovitch cycles, which actually preceded the age of reptiles and then occurred after the age of reptiles. And then I'll focus a little bit on satellites, starting with Sputnik and then going to NASA's unparalleled suite of observations, which has enabled a comprehensive understanding of the Earth from space. The age of reptiles lasted about 180 million years. That's a long run by any standard. And it was then, it ended with the Cretaceous Tertiary impact, which everyone is familiar with. But most people don't realize that the age of reptiles was preceded by probably an impact event at the end of the Permian Basin equal in magnitude to the Cretaceous Tertiary impact. And that provided the space for reptiles to radiate evolutionarily and then established their dominance for 180 million years. Then I'll talk about the Cenozoic era, 65 million years after, which started at the KT impact, and then come to the present. And in that discussion, I'll show a few slides on Milankovitch cycles, satellites, NASA, and then I'll conclude by showing that we need to modulate our use of fossil fuels, or we're going to be headed back to the Cretaceous rather quickly, much more quickly than we got out of conditions such as we had climatically at the end of the Cretaceous. Next. I'm fascinated, like so many people of all ages, about the age of reptiles. And this lasted for 180 million years. Here is a picture of a mural at the Peabody Museum at Yale. I've never been there, but the next time I'm close to New Haven, I'm going to go and see it in person. It's a massive mural over the age of reptiles, and this shows some of the reptiles from the Cretaceous period. Next slide. So if we look at the age of reptiles, this started about 245 million years ago, and it continued to 65 million years ago. And it was started by an impact at the end of the Permian, which was a huge impact or some extinction event, where on the order of about 70% of all marine and land animals perished, plants as well. Then there was a minor extinction event between the Triassic and the Jurassic, and then there was the major Cretaceous tertiary impact at the end of the Cretaceous, which all of us are aware of. And from that impact, about 75% of all plant animal species went extinct. Next slide. So let's start in the age of reptiles with the first period, which is the Triassic period, and that went from 250 million years ago to 200 million years. And this is what some of the animals looked like. Now, I put at the bottom where the impact was between the Permian and the Triassic. And so the Triassic starts after that impact. Next. This is what the Earth looked like at that time. Most of the continents were concentrated into Pangaea and also Siberia. And during the Triassic, it was temperate, it was dry, and there was no ice anywhere on the planet. Next. Now we make the transition to the Jurassic period, and this is when the dinosaurs came into their heyday, because it was moist, it was warm, there was no ice anywhere on the planet, and it was a perfect habitat for cold-blooded animals, and they reached enormous proportions and a tremendous diversity. Next slide. In the Jurassic period, the continents were starting to break up, and this is what they looked like. You can see it's quite different from today. And as I said, this is warm, wet, and no ice anywhere on Earth. A perfect environment for cold-blooded animals. Next slide. Now we come to the heyday of the age of dinosaurs, or the age of reptiles, and that is the Cretaceous period. And we all know about T-Rex. A T-Rex has been described as the James Dean of dinosaurs. He was big, he was fast, and he lived hard, and he didn't live very long. Because unlike some of the dinosaurs, T-Rexes usually only lived perhaps 30 to 40 years. And there were other dinosaurs like the sauropods, which people feel could live for up to 100 years. So there was a wide variety of dinosaurs, big, small, armored. We had all these amazing pterosaurs and pterodactyls flying around. I wish I could go back sometime in a time machine to the Cretaceous period and just see them, even for a few minutes, would be a tremendous experience. Next slide. Now, this is what the Earth looked like in the Cretaceous period about 100 million years ago. The continents were in the process of breaking up, and then migrating. So in the upper left is what the Earth looked like 110 million years ago. There was a very high CO2 concentration, about 1,000 parts per million. No ice anywhere on the planet. No ice sheets, no glaciers, no sea ice. Sea level was about 300 feet higher, and the average surface temperature was about 80 degrees Fahrenheit. In comparison, if we look in the lower right-hand corner, the present Earth, the continents are in the positions we know them now. The atmospheric CO2 concentration is now about 415 parts per million and increasing. We still have glaciers, sea ice, and the ice sheets of Greenland and Antarctica. We have the present sea level, and we have an average surface temperature of about 60 degrees Fahrenheit or 16 degrees centigrade. Next slide. Now, at the Goddard Space Flight Center 9 years ago, one of our local dinosaur authorities found an unusual collection of dinosaur footprints and mammal footprints from about 100 million years ago. And we call this our Rosetta Stone of the Cretaceous. And let's have the next slide. So these are some of the amazing tracks which Ray Stanford, who is an accomplished paleontologist, found on his original find, which we only thought when we found it, there were just 1 or 2 tracks. It turned out there were many tracks. There were over 100 tracks of dinosaurs and mammals, and here we have a few. And what is curious on this, or interesting, is we have mammal tracks and we have dinosaur tracks together. And in amongst the mammal tracks, there are 4 trackways of small carnivorous dinosaurs who were hunting our ancestors. We also have pterosaur tracks, and one of the coolest tracks on what we found at Goddard is there is a parent nodosaur, and there are 2 baby nodosaur tracks in the footprint of the mother or the father. So they were walking together, and when you have a trackway to study like we have here at Goddard, you can infer behavior, and it looks, and we see again and again that there was communal activity of dinosaurs operating as groups, or in some cases hunting as groups. Next slide. So just to go back, in the Cretaceous period, it was very warm. In the upper left-hand corner, 110 million years ago, high carbon dioxide concentration, no ice on the planet, sea level 300 feet, 100 meters higher, high average temperature of about 80 degrees Fahrenheit, versus the present situation where we have a much lower carbon dioxide concentration. We have glaciers, sea ice, ice sheets, present sea level, and an average surface temperature of about 60 degrees Fahrenheit or 16 degrees centigrade. Next slide. So now let's come to something which I find utterly fascinating, and that is the end of the Cretaceous period. And this was caused by an asteroid which collided with the Earth and what is now the area of Yucatan in the Gulf of Mexico. So this shows what it must have been like, I think. Here we have the dinosaurs running around, pterosaurs flying around, and suddenly this asteroid comes streaking through the sky before it crashes into Yucatan. It must have been very frightening. There must have been sonic booms as this was traveling at a very, very high rate of speed, and the asteroid was somewhere from 10 to 15 kilometers in diameter. Next slide. So the impact of this asteroid in Yucatan had the force or the power of about 100 million nuclear bombs. And again, this is from a 10 to 15 kilometer diameter asteroid traveling at about 20 kilometers per second or 12 miles per second. So it was really, really flying along. Next slide. Here is another artist's rendition of the impact of the asteroid just as it starts to hit Yucatan. This was a very big event. It caused shock waves, it caused tremendous tsunamis, and it also injected into the atmosphere a huge volume of debris and aerosols, which ended up blocking the sun for a while. Next slide. This is an artist's reconstruction of the impact. It is about 180 kilometers in diameter on the coast of the Gulf of Mexico in Yucatan. And this was one big impact. Next slide. Now, what happened after the impact is represented in this graph. So if you look on the left-hand side where it says temperature, you notice things come along a dotted green line with the red line, and then at the point of the impact, things immediately shoot up because instantaneously over the course of a few hours, the impact blew a lot of superheated debris into the atmosphere. This then came, or the larger pieces in this came down and started forest fires, massive fires, and this warmed the atmosphere, and then you had all these fires that were burning. And so the next slide, please. We're all familiar with nuclear winter, but there's a new term which I discovered, which is called microwave summer. So after the impact, the first event which occurred, which was highly unusual, was the microwave summer. The Earth heated up tremendously. There were fires, and this resulted in a huge volume of material in the stratosphere, which blocked the downwelling solar flux from coming to the Earth's surface. So there was no sunlight, there was no photosynthesis for at least 1 year. This resulted then in cooler conditions over a period of time of several months before things started to warm up. So during the cooler period caused by nuclear winter, all of this material in the upper atmosphere that blocked the sun like a giant sunscreen, the continents were cooler by 20 to 30 degrees centigrade, and the oceans were cooler by 10 degrees centigrade. So this was a massive cooling, and it was due to blocking all the downwelling sunlight for at least 1 or 2 years. Then gradually things recovered. Next slide. So one of the consequences of the KT impact was it caused the demise of the dinosaurs, but this gave rise to the age of mammals, to our ancestors. And the animals which survived the KT impact, let's go to the next slide, were animals, they were all small. There were no large animals which survived the KT impact. There were animals, the animals which survived were less than 50 pounds. They also could eat detritus, or dead plant material, because there was no photosynthesis, there were no herbivores, there was nothing for carnivores to eat. It was advantageous to be burrowing like turtles or our mammalian ancestors. It was advantageous to be water dwelling like crocodiles, turtles, and horseshoe crabs. And it was advantageous to be mobile like the birds. So these are 5 of the animal groups which survived the KT impact. And of course, we come from the mammals which survived, although they then radiated into many, many different mammalian life forms. So we were very fortunate that our ancestors could exist on detritus, lived in burrows, and here we are today looking back and reconstructing what happened. Next slide. Now, when the KT impact theory was published by Luis Alvarez and his son Walter Alvarez in 1982, they were attacked by a huge number of people who told them they were completely wrong. There was no basis for saying this had happened. The age of dinosaurs had ended very suddenly. We now know otherwise. Now, in this photograph, the person on the third from the right or second from the left is Walter Alvarez, who is the geologist son of Luis Alvarez. And so he was ridiculed, attacked stridently from 1982 through 1986, 1987, and then gradually more evidence accumulated. And then more recently, 2 young geologists and paleontologists, Robert De Palma and David Burnham, who were on the far left, and in the center is Robert De Palma. Robert De Palma found a site in North Dakota, which is an impact site which has a wide range of plant material, different types of fish, and different types of dinosaurs, which were buried on the day of the KT impact. And this is an amazing site. We've had one of our scientific colloquia virtually so far on the site. We will have another one in the fall, or maybe two more, because there's so much material coming out. And the gentleman on the left is Jan Schmidt, who is a Dutch paleontologist. He also found evidence of the KT impact in the iridium layer, which is the smoking gun, and this is all around the Earth. And it's from this that the establishment of the KT impact as fact and not fiction, and the super nuclear winter, which it caused, preceded by the microwave summer. This is extremely interesting. If anyone is interested, you can find numerous things online about De Palma and Burnham and their Trena site in North Dakota, the day of the KT impact. Next slide. So these are some of the things which De Palma and Burnham and their team have found at the Trena site. First of all, many paleontologists didn't want to work at this site because it was too confusing. There were freshwater fish, there were marine fish, because where the site is in North Dakota was formerly on the edge of the inland waterway at this time, 66 million years ago, in North America. And so there were freshwater fish, and this is a slide of some of the freshwater and saltwater fish fossils, which they found at the Trena site. Next slide. Now here is a picture of Robert De Palma, and he's pointing to the Cretaceous layer of where the extended finger on his right hand is. So this is just an amazing site, and it is the day of the KT impact. Next slide. Now this, one of the many smoking guns which De Palma and Burnham and their team have found are that many of the fish which they found fossilized, they had died suddenly. They had never been scavenged, and they had actually been asphyxiated by a huge volume of microtectites, which you see here. You see a person's finger or hand, and then on them are all these small modules. When there's an asteroidal impact, there is a huge a deposition of material which was present geologically, which is vaporized or heated to very, very high temperatures, blown into the atmosphere, and when it comes down, it reforms into a solid, and those are called tektites. And De Palma and Burnham found that the fish at this site had been smothered because their gills were completely covered with these microtectites. So this is the smoking gun, and the chemical composition of the tektites is exactly that of the parent material in Yucatan where the impact occurred. Next slide. So the KT impact ended the Cretaceous period. So now let's talk about the time of period, or the period of time from the KT impact to the present. And anytime you have to use proxies to reconstruct something like the atmospheric carbon dioxide concentration, this is very difficult because the further back you go, the more uncertainty you have in all of your proxies. So this is the best reconstruction from Berlin and Royer, 2011. And you see the carbon dioxide reconstruction with a lot of variation. But you notice that things first increased for a while, and then we've had this gradual decrease in terms of atmospheric carbon dioxide. And then above the CO2 plot at the bottom of the page is a corresponding temperature graph showing how the temperature followed. Now the temperature data are from reconstructions of O18 of oxygen 18 and oxygen 16. So that's one proxy which is used, and you have much more stability and less variation in the retrievals using one proxy as compared to many which you have to use for the carbon dioxide reconstruction. Let's look at the temperature trend in more detail in the next slide. This is how things look. So these are the same data. This is from Zakos et al. 2011. And again, it's based on oxygen 16, oxygen 18 isotopic ratios. You see that I draw your attention to about 50 million years ago, which coincidentally is the time when India started colliding with Asia. Plate tectonics are very important in the history of the Earth. And then you notice this gradual decrease in temperature from 50 million years ago to the present time. And you also notice that I've inserted in this graph two interesting aspects of these temperature decreases. One, the top one, is the Antarctic ice sheet started to form when the temperature was low enough, and that corresponded to a carbon dioxide concentration of about 450 parts per million. And then I have noted from other evidence that the Greenland ice sheet started to form when the atmospheric CO2 concentration was 400 parts per million. And this will be very important later when I talk about our possible return to Cretaceous-like conditions on Earth. Next. I really like this slide. It's cool. It shows continental drift. And what it shows is India, in its path across the Indian Ocean, has now collided with Asia, and that has forced up the Himalayan mountains. And so people did not accept continental drift until the mid or late 1950s. It was proposed earlier by Alfred Wagner, but evidence like this, looking at sonar and the floor of the ocean, shows conclusively a continental drift. And here we see the evidence of India's trip from further south as it collided into Asia. Next slide. Now, people have previously assumed that the weathering of silicate rocks, which produces bicarbonates, which can be buried in the ocean, was the mechanism for lowering the atmospheric carbon dioxide concentration and hence reducing temperature. This has been caused into question recently. It could just be a coincidence in time, but this is one theory which has been advanced and was getting to be pretty well accepted before a paper or two came along questioning it. So we don't know what happened. It could have been coincidence, or it could have been this silicate rock weathering, which results in cations and bicarbonates being buried in the oceans. Maybe not. More will be coming out on this shortly, I'm sure. Next slide. Now we know that atmospheric composition is really important. And this is and I have this in a spreadsheet if anyone would like it. You take the solar flux at the photosphere of the sun, you propagate that to Venus, the Earth, and Mars. You assume no atmosphere. We know from planetary observations what the reflectivity and absorptivity of the three planets are. The reflectivity is called the albedo. And from the energy absorbed, you can calculate what the surface temperature should be without an atmosphere. So you do this for Venus, and the surface temperature should be 64 degrees. You do it for Earth, our temperature should be about 0 degrees Fahrenheit. And you do it for Mars, and the temperature on Mars should be about minus 90 Fahrenheit. The actual temperature on Venus is something much, much higher, on the order of 860 degrees Fahrenheit or 465 degrees centigrade. The Earth's temperature is about 61 or 62 degrees Fahrenheit. That is 16 degrees centigrade. And the temperature on Mars is about what you would expect with no atmosphere. And that's because the Martian atmosphere has been blown away by the solar wind. And the actual temperature on Mars is about minus 80 degrees Fahrenheit or minus 60 degrees centigrade. So having an atmosphere is really important, and carbon dioxide in the atmosphere being one of the greenhouse gases, that concentration is fundamental to regulating temperature on those planets. In the case of Venus, Carl Sagan, one of the first papers he wrote on planetary atmospheres was he postulated that the high temperatures on Venus were due to a runaway greenhouse effect, which is accepted now. Next slide. Now, we have been making atmospheric CO2 measurements and discerning or learning or seeing how they affect temperature since the late 1850s, when a lady scientist, Eunice Foote, put thermometers into clear glass vessels which were sealed, which had carbon dioxide in them, and she noticed the more carbon dioxide in the cylinders, the higher the temperature would be, as shown by the thermometers. Now, we all know that women's contributions to science and in fact many areas of our common Homo sapiens heritage have been neglected, but she was the first person to do this. And she's now recognized in the same way that we recognize Professor Arrhenius in the center photograph, who won the Nobel Prize in Chemistry, and also Charles David Keeling, who started our present day atmospheric CO2 measurements on top of the Mauna Loa volcano in late 1958. And I show, as of February, the average February 2021 carbon dioxide concentration was about 417 parts per million, and in 2020 it was about 414 parts per million. This is because we're burning fossil fuels. I again show that there's reason for concern that now that we are above 400 parts per million, we are destabilizing Greenland. And if the temperature rises above 450, or if the CO2 concentration rises above 450 parts per million, this may destabilize Antarctica, not because of the CO2 effect, but because of the carbon dioxide causing higher surface and atmospheric temperatures. Next slide. Now let's talk about Milankovitch cycles. These are named after Professor Milankovitch, who lived from 1879 to 1958. So he lived before the time of digital computers, and he worked out the Milankovitch cycles longhand from first principles. Next slide. Now I'll jump to some ice core data, because the ice core data are like time machines. And I'll talk about a 440,000 year ice core from Antarctica, but we also have a longer ice core record from Antarctica, 800,000 years, and we also have from Greenland a 120,000 year record. But I will be talking about the Vostok Ice Core from Antarctica, which is 440,000 years. And on the right-hand side, you see what the core looks like. It comes out. It's very unimpressive. But because this is 2 miles of ice which has been drilled out, and you save what is within the core, within the tubing, you have a 2-mile time machine for the reconstruction of climate. Next slide. So now I will show some results. This is from Jim Hansen, but others have also published this, where you notice, so you have an ice core. And the first thing you have to go through is you have to go through and date the periods in it between summer and winter conditions. And you also have various volcanic eruptions, which enable you to reset your chronology if you're off slightly. So once you have the core dated in terms of the chronology of the core with depth, you can then go in and you can do several things. You can extract water from each of these time periods, and from an oxygen 16, oxygen 18 isotopic reconstruction, get the temperature. You can also drill in and get tiny bubbles that are trapped in the ice, and from those you can extract the carbon dioxide concentration and the methane concentration with respect to time over the length of the core. And so we see here that the temperature record at the bottom in red is synchronous to a very, very high degree with the methane concentration in the atmosphere and the carbon dioxide concentration in the atmosphere. And you'll notice on the right-hand side, we're now at about 417 parts per million carbon dioxide. Next slide. So now, one of our former great scientists at the Goddard Space Flight Center, Norton Huang, and his colleague Zahua Wu published a paper in 2008 in the Review of Geophysics, where they used the Hilbert-Huang transformation, which is a nonlinear, non-stationary time series reconstruction tool, which can be used on any digital signals, and it breaks things down into different frequencies. So once you have an ice core dated, you can treat the carbon dioxide data, concentration, the temperature, or the methane value as a signal, and then you can see how that varies with respect to time in the core. And so you use the same technique to get rid of static in cellular digital communications when we speak on the telephones. So the very same technique is used there. So you break the data down, it is adaptive, and so you break data down into different frequencies, and so, or different periodicities. So this is the first 8 periodicities, which are not very interesting with respect to the Milankovitch cycles. Let's go to the next slide. But we see from Huang and Wu's decomposition that decomposition component 9 at 22,000 year periodicity, and component 10 at about 40,000 year periodicity, and component 11 at 100,000 year periodicity. These are 3 of the Milankovitch cycles and their periodicities. Let's go to the next slide. So let's look at eccentricity. Eccentricity is simply the non-circularity of the Earth's orbit around the sun. And this varies with a periodicity or frequency of about 100 to 110,000 years. So now we have taken the reconstruction of eccentricity of that component from Norton Huang and Zahua Wu's paper, and we have superimposed it upon the temperature anomaly data from the core. And we'll see that it matches up slightly. Now let's add the other 2 orbital components and see what happens. First, we will add obliquity. The Earth is off axis. It varies over a few degrees with a periodicity on the order of 41 to 42,000 years. And when you add in the component for obliquity, the red line matches up much better with the curve. Now let's add in the 3rd component, which is precession of the equinoxes, with a periodicity of about 10,000 years. So next, please. When you add in these 3 components of the Milankovitch cycles, eccentricity, obliquity, and precession of the equinoxes, you then match up very well with the temperature data. And so you have these periodicities of 20,000 years, 40,000 years, and 100,000 years. There's also a eccentricity component at 400,000 years, but with an ice core of only 440,000 years, it's not possible to extract that data. So you see this perfect, or this very, very highly coincident proof that the Milankovitch cycles are what drives the ice ages, the interglacial periods, and there's no question about that now. Now let's look at all of the other components which have come out of Huang and Wu's work. Next slide. So these are all the shorter frequencies, and you'll notice that they are much more numerous and better represented further up on the core, and that's because you're dealing with periodicities on the order of 10 years, 50 years, 100 years, and the deeper you go in the core, the more the data become compressed and the more difficult it is to extract these high frequency variations. So you can think of the red line here. This is weather, whereas climate is in the blue, showing the long-term variations over a much longer time period. And indeed, you can use the Huang and Wu technique for studying climate, and it is a climate tool, but it is perfectly suited for ice core work and breaking out the Milankovitch cycles. Next slide. Okay, so now we have gone from dinosaurs to Milankovitch cycles, and now let's go to the space age. So on the 4th of October 1957, I remember it well. I was 11 years old at the time, in school, and it was announced that the Russians had launched a satellite into space. Well, no one knew what a satellite was, but we learned very quickly. It was Sputnik. And this started the space age of putting satellites into Earth's orbit to study the weather, to study the oceans, and also to look out from the Earth for planetary astronomy, for astrophysics, for heliophysics. The use of satellites has revolutionized science in the 21st century. Next slide. Now, one of the really cool images which I like is this image from Voyager 1, taken on Valentine's Day of 1990 from 6 billion kilometers away. So this is a huge distance. It's on the order of between 3 and 4 billion miles from Earth, and this was beyond the orbit of Neptune. Let's have the next slide. And what was observed is where the blue arrow was pointing, that dot, that's Earth. And Carl Sagan was on the science team, on the imaging team for Voyager 1 and 2, and he was instrumental in getting the imager pointed back at Earth. People said, well, you can't see anything. He said, let's look anyway. And so what you see is the pale blue dot. That's here, that's home, that's us. This is where we make our stand. So this is another way of looking at Earth. Earth is the only planet we know which harbors life. This is highly unusual in our study of space. In fact, we've found no other place. Life may have existed on Mars, but there's no life there now. Next slide. This is a picture I like very much. It was taken by my late dear friend Pierre Sellers, who worked at the Goddard Space Flight Center, who then left, went to become an astronaut, and then came back to Goddard after the shuttle program ended. This is a sunrise looking from the International Space Station or Space Shuttle towards the horizon, and that very narrow light blue and dark blue band, the very narrow light blue and dark blue band, that is our atmosphere. This is what makes the pale blue dot pale, is we have an atmosphere. Next slide. Now, within NASA, we have many satellites which study the Earth. One of my favorites is SeaWIFS because it studied at the same time the oceans and the land. And this is an image which Gene Feldman and I put together of the global biosphere from SeaWIFS. We see the land, we see the oceans, and because we're interested in the oceans and land, we got rid of all the clouds. I apologize to all of my atmospheric friends, but I could easily have shown any number of very cloudy images, and I'll be happy to in the future. Next slide. Now, what Pierre Sellers and Carl Sagan and in fact, all the astronauts I've talked to, and I've talked to several who were Pierce's friends, they all say the same thing. The Earth is a very precious place. We're all in this together. It's one planet, one climate, and this is where we make our stand, and we have to deal with things ourselves. We can't wait for help from anywhere else. Next slide. The Earth has an amazing biota. It did in the age of dinosaurs, and it does now in our present time. Here are two charismatic zebras, a mother and baby zebra. Next slide. So we have a very interesting Earth. Now, this is to sort of tie things together. We see Tyrannosaurus Rex up at the top on the center left, and then in the middle left is Albert Wagner, who postulated continental drift. Below T-Rex's head is Professor Milankovitch, and below Professor Milankovitch is a fellow named Harry Hess, who was a geophysicist, I believe at Princeton, and he was also an admiral in the Navy. And in the Navy in World War II, he was the captain of a ship that had a sonar, and he left the sonar turned on wherever it went, and he mapped the ocean bottom. And the work of Harry Hess and others using sonar data was instrumental in confirming continental drift. Then we have Sputnik on the right-hand side. There are two photographs of Sputnik, not very impressive. Well, actually, one is Sputnik and the other is an early American satellite. But this is when the space age started. And then below that, we have Dave Keeling with his atmospheric carbon dioxide measurements from Mauna Loa in Hawaii, which show the breathing of the biosphere. This is one of the iconic Earth science data types, which is continued to the present. Next slide. Now we know the Earth is warming, and we know this largely because of satellite data. We know that sea level is rising because of satellite data. We know the sun is remarkably constant and has been ever since we had satellites above the Earth's atmosphere, which could observe the sun with no atmosphere. We know there's no change in the sun over this time period, and solar physicists have extended these data back now for almost 1,000 years, and they find the very same thing. We know that ocean temperatures are increasing. We know that in terms of sea surface temperature, but we also know it with depth from the Argo measurements. Argo is not a satellite. Those are a collection of autonomous buoys. We know from surface thermometers and atmospheric soundings that surface temperatures are increasing and atmospheric temperatures are increasing. And we know from satellite data that glaciers are melting and that sea ice is melting, and we're also losing ice from the ice sheets. Next slide. At the present day, some people think they can define things any way they want and it has relevance. I always refer them to this quote by Confucius, that unless you have proper definitions, logical discourse is impossible, and without logical discourse, nothing can be accomplished. This is very important. This is fundamental to science. Next slide. We make measurements from satellites of geophysical variables, geophysical measurements. Radar, gravity, and temperature are three of those. Next slide. This is work of Judith Lean, a friend of mine from the who is a heliophysicist. And what her work has shown is the total solar irradiance is very constant, not only for our period of observations, but in a paper of hers, she has extended these data back to 850. So back from 2000 to 850. And what you see is that people who attribute a warming Earth to variation in total solar irradiance are simply mistaken. They're wrong. And the work of our solar physicists shows this unequivocally, not only for the period of direct observation, but a very careful reconstruction using beryllium-10, carbon-14, other proxies, as well as the sunspot records going back through time to 850. Next slide. Now, we know the best indicator of global warming is sea level. And we measure that with radar altimeters on satellites. This is what it looks like. We have these data started in 1992 and have continued through today and are continuing. Next slide, please. What these satellites do is they send down thousands of pulses of radar signals a second as they orbit the Earth. You can take these data and process them into sea level. This is what the data look like. I won't go into the particulars on this. It would take me 10 or 15 minutes to explain this. I explain sea level in my talks on geophysical measurements, but for the purpose here, I'll just show, these are what the data show, and they result from 50% of the increase with respect to time. And so the increase is on the order of 3.5 centimeters per decade, or 3.5 millimeters per year. And so this is showing how the sea level varies in terms of millimeters per year. Half of the increase in sea level is due to melting of ice on the ice sheets, and half is from warming seawater, which expands as it warms. Next slide. Now, this is a really cool project where people have figured out how to determine what the temperature profile of water columns are in the ocean by using almost 4,000 of the Argo floats. These are autonomous, they're not powered, they drift, they're dropped off of ships. On the left-hand side, you see a graduate student with one of the Argo floats. Then in the picture on the right, you see the float floating in the water, the boat that deployed it. Then the boat goes away, then the float descends to 1,000-meter depth, taking periodic temperature and salinity measurements. It then drifts for 9 days, again taking periodic temperature and salinity measurements. It then descends to 2,000 meters depth, taking salinity and temperature measurements. Then it surfaces very slowly, again taking measurements. When the float reaches the surface, it has a burst transmission to a geostationary satellite. All the data come down into Argo Central in California, where they're processed and where all the instruments are calibrated. Now with Argo, on the 28th of October 2020, and the same would be true today, there were 3,932 floats actively operating on that day. This is how we get the temperature profiles of the ocean in a comprehensive way over all of the planet's oceans. Next slide. So that takes care of thermal expansion of seawater. There was an experimental NASA satellite called the Gravity Recovery and Climate Experiment, or GRACE. These were two satellites in an identical orbit, separated by 220 kilometers. They were orbiting the Earth at 500-kilometer elevation, and they had a radar on board which could tell their distance between them to 0.001 millimeters. And what these satellites read out as they orbit the Earth are variations in the separation between the two satellites, which is directly related to the gravity field beneath them from Newton's gravitational formula, which is listed on the lower right-hand portion of this. These variations can be converted into mass units, into weights, very easily. Next slide. Now, this has been done by two of my co-workers at the Goddard Space Flight Center, Brian Loomis and Scott Lutke, and their co-workers. These are data from Greenland, which show the mass variation or the loss of ice with respect to time from GRACE, from the first GRACE and from the GRACE follow-on satellite mission. You notice there is a decrease, and then there's an increase. The decrease occurs in the summer, the increase in the winter. So you show mass accumulation and mass loss. But in this case, you show a net mass loss over this time period of 2002 into the start of 2020 of about 273 gigatons per year. That's water which is flowing, either melting and going into the oceans, or icebergs which are calved and go into the ocean. And this is the ice sheet mass loss from Greenland. And this is because we can use satellite gravity data to get these measurements. Next slide. Now we see the same data for Antarctica, where the loss is much less. It's only 121 gigatons per year. But again, this is based upon gravity data, and most of the loss of mass in Antarctica comes from West Antarctica. From West Antarctica, as you see here. Let's look at West Antarctica in more detail. Next slide. Here we have a traverse going across Antarctica from A to B. A is where we have West Antarctica, and B is where we're in East Antarctica. Now, if you look at the bottom graph, what you see is the grounding of the Antarctic ice sheet in West Antarctica. An appreciable part of it is below sea level. That is not the case in East Antarctica, where most of the ice sheet, almost all of it, is above present-day sea level. So as oceans rise, you have warmer water interacting with the West Antarctic ice sheet. This will be a major cause of melting, and this is one of the concerns which our friends in the cryosphere area are using or are focusing on right now to see what is happening. It's very important. Next slide. Now, this is just, there are people called climate change deniers who argue against radar, who argue against gravity data, who argue against temperature data. I don't believe there's anyone who will argue about you need to know the gravity field, especially if you launch a satellite or if you fire a ballistic missile from point A to point B. Newton's gravitational formula is extremely well established. Anyone who argues against the gravity data, I think, is insane. Next slide. Okay, so we've seen about losing ice. Ice is nature's best thermometer and most unambiguous indicator of climate change. Ice asks no questions, presents no arguments, reads no newspapers, listens to no debates. It is not burdened by ideology and carries no political baggage as it changes from solid to liquid. It just melts. This is a poem by a geophysicist now retired from the University of Michigan, Henry Pollack. Next slide. So where are we headed? Well, we're actually headed back towards the Cretaceous because temperatures are increasing. And this is because of increasing fossil fuels in the atmosphere. And the rate of increase, as you can see here, is several orders of magnitude faster than the rate of decrease over the past 50 years. And it's highly likely the rate of increase will accelerate from feedback mechanisms. So this is what we have to work towards to minimize our use of fossil fuels, to reduce the atmospheric carbon dioxide concentration so we don't further destabilize Greenland and destabilize Antarctica, or else sea level will rise. Next slide. Here's Earth. It's here, it's home, it's us. This is where we make our stand. Next slide. Here's the pale blue dot from which what I just said was used by Carl Sagan to describe what he was looking at. And the last slide, please. Why NASA? So within NASA, we use space for exploration and scientific discovery, looking up, looking down, and looking forward. Thank you for your attention. I'll be happy to answer any questions.
Virtual round of applause. Thank you so much, Dr. Tucker, for that great presentation. Thank you, thank you. So we've got a couple minutes for a few questions. So I'm going to start quickly. So there's a 5-year-old that couldn't make it today, but he's wondering, what would a T-Rex dinosaur think about today's climate?
Well, it's getting warmer, and he would probably be in the southern part of the United States or close to the equator. That would be a perfect place for T-Rex to live because it would be warm and moist. And those were the conditions when T-Rex was thriving.
Great, and thank you for that question. Next question, is it true that dinosaurs were covered in feathers like birds?
Some were and some weren't. For a while, people thought that no dinosaurs were feathered, and now people have found feathers in fossils, paleontologists, and so that's established. And so very clearly, many dinosaurs were feathered, but some were apparently not.
Thank you. Next question. What was it about the environment that allowed the dinosaurs to grow so large?
Well, it was warm, it was wet, and then the age of reptiles was preceded by a very large impact event or some extinction event, which left all of these avenues for growth open to them because it killed off everything else. It killed off 70% of the existing marine and land animals. So they simply took advantage of these opportunities. It was warm, they were cold-blooded for the most part, and it was warm and wet, and they radiated evolutionarily and thrived.
Thank you so much. And this will be our last question. What do you mean about runaway greenhouse effect?
Well, on Venus, you get into a situation where you have so much carbon dioxide in the atmosphere that as conditions get warmer, you have more water vapor in the atmosphere, and then you have a feedback which operates, which makes everything hotter, which continues to make everything hotter. So a feedback is when something is set in motion, and then it amplifies whatever the trend was and makes it more.
Great. Well, thank you so much. And thank you, viewers, for joining us today. And remember, next week we've got 2 talks, so please join us again. Once again, Dr. Tucker, thank you so much for this excellent talk.
You're welcome.
Everyone stay safe, and I'll see you next week. Thank you very much and have a great day. Thanks, everyone. Bye.